You know, everything is easy if you know what you're doing, right? So let's look at something familiar by area of plane regions that we've talked about quite a bit. So if f of x is going to be greater than or equal to 0 for all x in the closed intervals including a to including b, and if f is integrable, then the area under the curve f of x bounded by that curve, the x-axis, and the lines x equals a and x equals b for the left and right boundary lines is going to simply be given by the area equals the definite integral from a to b of f of x with respect to x, which is why I said f needs to be integrable. So let's look at a couple examples. We've actually known this before. Let's look at the area under the curve f of x equals x squared on the closed interval 2 to 4. Well, if I draw a picture of this, I know that x squared looks like this, and then from 2 to 4 it arcs up like that. So basically what I have here is this area from 2 to 4 underneath this curve, and I want to come up with the area of this plane region right there, right? So the nice way to do that is just simply take the definite integral from 2 to 4 of x squared with respect to x, right? So we know that x squared is greater than or equal to 0 on that closed interval. So right there's the function f of x, and then trying to come up with that area, this is just going to be x cubed over 3 evaluated from the lower bound of 2 to the upper bound of 4. I know before I was putting a little bracket on there, but I like to just do a straight line, save a little time there. Plug in 4, and we get 4 cubed divided by 3. 4 squared 16 times 4 is 64. So this equals 64 thirds minus, and then if I plug 2 in, everywhere there's an x, it's going to be 2 cubed over 3, which is 8 thirds, and thus the area is 56 thirds square units, and you can either write it out as square units or u to the second power. So I'm just going to put u to the second power, but really that's units squared there. So we do need to say square units when we talk about area, unless we have a specific measure like feet or something of that nature. So we have a nice, real quick, easy way that we can come up with that definite integral versus something like you know, taking inscribed or circumscribed rectangles like we've done in the past, or Riemann sums. But that's where all this comes from. Now let's look at the next example, f of x equals sine of x on 0 to pi. So notice 0 to pi for sine of x. If I do this sine graph right here, that actually goes over to 2 pi, which I don't want to go that far. So here's pi right here. So really, I'm looking for this area right here. So what's the area under that curve from 0 to pi? So I don't need that part yet. I'm going to come back to that, and we're going to talk about area underneath of the x-axis. But in this case, going from 0 to pi here, this area is simply going to be the definite integral from 0 to pi of the sine of x with respect to x. So we know, by the way, anytime you have a polynomial function, it's continuous on all real numbers, so it's going to be integrable, right? And we also know that sine and cosine functions are continuous as well, because you can draw them forever without lifting your pen. However, tangent functions are not. You got to be careful on where you're at there. But anyway, so any continuous functions by theorem are going to be integrable as well. So the antiderivative of the sine of x is what? Well, the derivative of what is sine? The derivative of cosine is minus the sine, so the antiderivative of sine is minus the cosine of x, and I'm going to evaluate this from 0 to pi. So what I need to do now is I need to pay a little bit better attention to that minus sign, and I can leave that minus sign out front as long as my trusty assistant makes sure that I put it into my answer when I'm done. So I can just consider minus the quantity cosine of pi. If I plug pi in, cosine of pi, that's all the way over here. Cosine is your x, that's -1. And then minus cosine of 0 would be over 1. So I'd have the opposite of -1, which is the opposite of -2, which actually equals 2. And in this case, I'm just going to write out the language square units. So the area of the sine curve from 0 to pi is exactly 2 square units. So that's kind of a neat, exact, really nice answer to a really awkward trig function, right? So now let's kind of go back and look at that and say, okay, well, what if f of x is below the x-axis? So let's go down under here, and f of x is less than or equal to 0 for all x is on there. Then what the area under the curve by f of x, which is now below the x-axis, the x-axis and the lines x equals a and x equals b is actually going to equal the opposite, because what we're going to end up with is a negative number, and I'm going to prove that to you over there. So the area is actually going to be the opposite of the definite integral from a to b of f of x with respect to x. Of course, this is also assuming that f of x is integrable from a to b, right? But instead of writing it like this, we could also say, instead of minus the integral from a to b, we could just say it's the integral from b to a of f of x with respect to x. So we could also write it that way as well, where we switch the limits of integration there as well, because that would give opposite signs. So I like to think of this as integrating it from right to left would give it opposite sign as well. So what I'm going to do is I'm going to erase this one here, and we're going to look at this same sine of x. Instead of on 0 to pi, we're going to look on pi to 2 pi. So what we notice, if I would have drawn my curve nicely, is that it should be the exact same size. It looks a little bit smaller, but trust me, that's just the bad camera angle there. So we know that this one is 2 square units. It's blue, so the red one should be exactly 2 square units. So let's look from pi to 2 pi. I'm going to put that in red here. So the area is going to need to be, since f of x, sine of x, is actually less than or equal to 0 on that entire interval, it's going to be minus the definite integral from pi to 2 pi of the sine of x with respect to x. So in this case, what is the antiderivative of sine is minus the cosine, so it's going to be opposite of minus cosine of x, and then evaluated from pi to 2 pi. Well, this works out nicely here that this minus and minus is plus, right? So this just ends up being cosine of x evaluated from pi to 2 pi. Plug in the 2 pi here, and cosine of 2 pi is all the way around. It's the same as cosine of 0, right? Which is the x value, which is actually 1. And then minus cosine of pi, when I plug that in, is halfway around. The x value is minus 1. So we subtract away a minus 1, and 1 minus a minus 1 is actually equal to 2 square units. So it worked out exactly how we thought it would, that the area here is 2 square units for this one, and the area of the top one is also 2 square units. So really what I want is, if I want the area of both of those, I would need to add those together, right? So we got to be a little bit careful adding those together, and I'm going to show you why here, and finish up and look at a couple of cautions that we need to throw out there. First of all, I'm just going to use black for this because this doesn't equal the area. But if I simply took the definite integral from 0 to 2 pi, and I went all the way of the sine of x with respect to x, let's see what we end up getting. This is going to be minus the cosine of x evaluated from 0 to 2 pi, and then plugging that in, it's going to be minus, I'm going to do the cosine separately here. So just plugging in 2 pi, cosine of 2 pi is 1, and then minus cosine of 0 is also 1. So it's going to be the opposite of 1 minus 1, which actually is the opposite of 0, which is 0. Now, I'm not going to put square units there because that's absolutely not the area. We know that there's actual area that's for the blue part, and there's actual area for the red part that's greater than 0. So there's no way that this is actually the area from 0 to 2 pi there. What it is though, is it is the value of the definite integral from 0 to 2 pi of the sine of x with respect to x. And the reason it ends up being 0 is because the definite integral from 0 to pi is considered to be a positive 2, and the definite integral from pi to 2 pi is negative 2. So when you add those together, we actually would get 0. So if we want to do the area, we have to do it one of two ways. We can split it up as what's above the x-axis and what's below the x-axis. So we can say that the area is going to be the definite integral from 0 to pi of sine of x with respect to x plus the negative integral, so the opposite of the definite integral from pi to 2 pi of sine of x with respect to x. So if I want the actual area, now if you add the opposite, that's the same as subtracting, right? So I could actually take the first one, which is positive, and then subtract away the next definite integral, which is negative, and that ends up being 4 square units. The other way we could write this, I could say the area is the definite integral from 0 to pi of the sine of x with respect to x, which gives us the positive 2 square units. And instead of subtracting from pi to 2 pi, I can take the opposite of that, which is add the definite integral from 2 pi to pi of the sine of x with respect to x. So I'm going to finish this video just verifying. We already know that the first part is the blue part is 2 square units. So let's just see if this adds another 2 square units to that. So let's actually evaluate it this way, which is really from right to left, and see what that ends up being. So the definite integral from 2 pi to pi is going to be minus the cosine of x evaluated from 2 pi to pi. And remember, it's plugging in the upper limit minus the lower limit, and of course I've got my minus sign out front, but when I plug in cosine of pi, is the x value over here is -1, and then I'm going to subtract, plugging in the lower limit, the cosine of 2 pi, which would be the equivalent to cosine of 0, is a positive 1, so I'm going to subtract away a positive 1, so it's going to be the opposite of -1 -1, which is the opposite of -2, which is actually a positive 2, and so there's positive 2 square units, just like we knew right there in that shaded area. So a couple of different ways you can do it. If we have some of your function ends up being above the x-axis and some is below the x-axis, we can split it up, but we do need to remember that area when your function is above it is going to be positive, and the definite integral, if it's below it, ends up being negative. So for area, we have to take the opposite of negative and turn it into something positive that we can use.